Hello, good day. This is Kevin, and I'm going to solve some differential equations problem. And I have here one xy squared plus y dx plus x minus x squared y dy. So as you can see, this is not exact. It can only be exact by multiplying by a proper factor. Such multiplier is called an integrating factor. So this equation, it can however written as x y squared dx plus y dx plus x dy minus x squared y dy equal to 0. So I'm going to group the dx and the dy. So here the x y squared dx minus x squared y dy plus y dx plus x dy equal to 0. Then for finding the integrating factor, if a first order derivative equation or differential equation contains the combination of y dx plus x dy, the function of x y as a multiplier to make the equation integrable. So I have here the integral to the integrating factor, which is equal to 1 over x y. I use this integrating factor to make the equation integrable. So I multiply the integrating factor both sides. So I have here xy squared dx minus x squared y dy x over y plus the dxy over is equal to, this is equal to 0. So after multiplying both sides, as a result, here y dx minus x dy plus dxy over xy equal to 0. So I'm going to multiply both sides again by the integrating factor, which is the integrating factor is equal to 1 over xy. So I have here y dx minus x dy over xy plus dxy over xy squared equal to 0. So I'm going to put the negative sign of x in the outside. So here, negative x dy. So if I'm going to put the negative on the outside, the negative y will become negative minus y dx over xy plus dxy over xy squared is equal to 0. According again the tips for finding the integrating factor, this function is minus 1 is equal to, when this function is equal to d ln of y over x. So plus d x y over x y squared. Next, I'm going to apply the integration. So I'm going to integrate this one and this one. So to integrate this, I'm going to let m equal to ln y over x, and I'm going to let this as u. Let u be x and y. So I have here the integral of dm plus the negative sign plus the integral of u negative du equal to 0. The integral of dm is equal to m. It's negative m plus the integral of u negative 2 is negative 1 over u plus c. It's the arbitrary constant. So my final answer is negative m minus 1 over u plus c, and m is ln, is negative ln of y over x minus 1 over xy plus c equal 0. So this is my final answer. Okay, my next equation is y prime is equal to negative 2xy. So this equation can be solved using separable. So let's go. Since y prime is equal to dy over dx equal to negative 2xy. So to separate, you have dy over y is equal to negative 2x dx. So by this, we can now integrate both sides. So integrate both sides, and the integral of 1 over y is ln of y is equal to integral of negative 2x is x squared over 2, so cancel 2, so we have negative x squared plus c. Since we have the answer of ln, to remove ln, multiply both sides by e. So we have y is equal to e to negative x squared plus c, or this is y is equals to e negative x squared times e to the c. We let e to the c as constant, so our answer is y is equals to c e to the negative x squared. This is our final answer. So our third problem is if m x and y dx is equal to n x and y dy is a homogeneous equation, prove that if it is expressed in terms of the polar coordinate r and theta by means of the substitution x equals r cosine theta and y is equal to r sine theta, it becomes separable. So to solve this, I'm going to write first the equation. Yes. M x and y dx is equal to n x and y dy. So since it is expressed in terms of the polar coordinates r and theta by means of the substitution, x is equals to r cosine theta and y is equals to r sine theta, I'm going to substitute the value of x and y. So I have now m the value of x, which is r cosine theta, and the value of y is r sine theta dx is equal to, since we don't have enough space, I'm going to squeeze now, n is r cosine theta and r sine theta dy. So since we have x is equal to r cosine theta, I'm going to find the dx. So we take the derivative of x, and that is equal to the dx is equal to negative r sine theta plus cosine theta dr. And since we have y equal to r sine theta, so the derivative, so the dy is equal to r cosine theta d theta plus sine theta dr. We solve this by using the chain rule. So substitute the value. since our m equal to r cosine theta and our y is r sine theta, and our dx is negative r sine theta d theta plus cosine theta dr. That is equal to n times r cosine theta r sine theta, and the value of our dy is r cosine theta d theta plus sine theta dr. So we're going to cancel out this. Cancel. So we now have the m negative r sine theta d theta plus cosine theta dr is equal to n. So n is r cosine theta d theta plus sine theta dr. So I'm going to next is I'm going to remove the negatives in the outside. So I'm going to distribute the value of m. So I have now negative m r sine theta d theta plus m cosine theta dr is equal to, and also the n distribute inside, n r cosine theta d theta plus n sine theta dr. And then after, so you now get the separable equation. This dr is equals to n cosine theta plus m sine theta over m cosine theta minus n sine theta. So the equation now is separable.